Hey guys, so sorry I wasn't able to make it to class yesterday, but here's the quick video on explaining derivatives as rate of change. So here's the main thing. We're covering average versus instantaneous rate of change, examples, graphing, and some common problems. One of the things that I really wanted to highlight is that as we're doing this, this is kind of like a first look at it. Right now, we don't have all the tools to really do solid problems on this, but we can start doing like just getting the general gist. So if you don't get it as of right now, it's not the end of the world. It's just kind of helping your brain to start thinking this way. So once we start doing antiderivatives, it makes a lot more sense because most of the AP problems, this is almost never touched outside of the context of derivatives and antiderivatives, so that you're only getting like half of what you need to know now. So again, if you get it, great. If not, it's not the end of the world. So as a clarification, one of the things that we want to remember is that derivatives are rates of change, instantaneous rate of change. You guys know how to find rates of change. Rates of change in general are slope. So when I say average rate of change, that's where we have this equation here, where we're saying end over start divided by total time. So for example, if I were to say something like, what's the average rate of change of the toy production of Santa's elves or something like that. I started off with 300 toys, I ended up with 500 toys, so that end minus start is 200. And how long did it take me to do that? Well, it took me 1 day. So we can say like, okay, Santa's workshop makes 200 toys in 1 day, but these are common slope problems. You've done it before. The main difference is that when we're doing instantaneous, we're trying to find like very specific rates of change. And a lot of times it's when there's these continuous rates of change and whatnot. So for example, we might say something like, what's the population in 2000? What about 2001? What about 2002? So on and so forth. And the rate of change might depend. Like, for example, in summer, a lot of people might move away, but in winter, less people move away. So it might flux. So it doesn't make sense to take these like endpoint rates of change. So that's when we take these instantaneous rates of change and we take the derivative. Now, if it says average rate of change, it's going to tell you average. So the only time you use this, if it says specifically what is the average rate of change. Now, when you're doing functions and stuff like that and taking derivatives, that's when it's instantaneous rate of change, but it'll just say what is the rate of change at given this time here. Okay, so again, one of the key words that you're dealing with when you're dealing with average rate of change, if it does not say average, you're assuming you're taking the derivative. Now, there are some special cases where it might say approximate the rate of change, which is basically the same idea, and it'll give you some sort of table. But again, we'll talk about that a little bit more once we're doing antiderivatives, because that's where it really pops into play. So when we're doing average rate of change, here's some of the examples that you guys can have. Mr. Mori was driving blah, 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 blah. What was his average velocity? People were voting for blah, 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 blah. On average, how many ballots came in, or how many more ballots were coming in, something like that. Water was filling a cup, blah, 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 blah. On average, over this time, how quickly was the height rising, right? Again, the word average is in all of these. If you're not doing average, then you're not taking slope. Instantaneous is something like Mr. Mori was driving and his position was given by this function. 5 minutes after he started, what was his instantaneous rate of change? Now, again, we talked about this when we first started talking about derivatives. We were saying something like, if I'm driving, I'm not driving 45 miles per hour the entire time. I'm driving 15 miles per hour. I'm stopped. I'm driving 60 miles per hour. And so the average rate of change doesn't make quite as much sense. People were voting for blah, 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 blah. When did the ballot, or when were the ballots coming in the quickest? So that would be something like, what was the biggest rate of change? And you have to find maximums and minimums. But again, the word average isn't there. Water was swinging, blah, 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 blah. 3 minutes after it started, how quickly was the height rising, or something like that? How quickly was the volume changing? And again, these are instantaneous rates of change. So basically, as long as you're not saying the word average, you're taking the derivative. So let's look at a really common example. The equation S equals 1/2 gt squared is used to find the distance from rest of an object in free fall, where S is the distance, g is the gravitational constant, and t is the time from free release. At sea level, the gravitational constant is 9.8 meters per second squared. So here's the question. If Mr. Mori were to drop a ball 30 feet from the ground, assuming near sea level, what would the ball's speed and acceleration be 1 second after drop? So basically what we're going to be doing is we're going to say, well, this is my position. If I want to find speed or acceleration, we're going to have to take the derivative. And acceleration is basically the rate of change of your rate of change. So that's kind of how this is working here. One thing to note, speed and velocity does make a difference. Speed is just the absolute value of your velocity. So if I were to get like -5 feet per second or something like that, then you would have to change it to 5 feet per second because it is asking for speed. So let's run through this really quickly. It says that S equals 1/2 g of t squared. And then we're going to take the derivative of this. So we're going to get S prime equals 1/2 g times 2t. Now, the question is, why don't we have to use product rule here? And because g is not a variable. In this case, we know what g is. It's a gravitational constant. G equals 9.8 meters per second squared. So just be careful of that. Just because it's a letter does not mean that it is not. Sorry about that. But just because it's a letter does not mean that it's necessarily a variable. Context really does matter here. So this is my S prime. And one of the things that I like to do is I actually like to label what it is. This is my velocity function. One thing that we have to remember is that it says the gravitational constant is 9.8 meters per second squared. The positive and negative does make a difference here. So basically it's saying as we're going down, that's our positive direction here. So that's just something to keep in the back of your mind. Again, right now we're just working on the overview. We're going to get into the nitty-gritty of it a little bit later. But for now, remember, what do each of these little pieces of information tell you? Positives and negatives make a difference. Where's the positive direction in this case? What does that look like? What's the difference between acceleration and speed? All of these types of things. Really, really important. So this is S prime, and then we'll do S double prime is going to be equal to just G, basically. Sorry, I should have canceled it out. So these cancel out, so we're just left with G of t. And that makes sense because what we know is that G my gravitational constant, is 9.8 meters per second squared. And that's the format that our velocity or our acceleration is supposed to be in. It's supposed to be in a meters per second squared kind of thing. So the question is, A, what is my velocity going to be, or what is my speed going to be 1 second after drop? So we're just going to plug it into this one right over here because that's going to give me speed. So we're going to say S prime is equal to 9.8 meters per second squared times by 1. So S 1 second. And again, the reason why we want to have that is so that way we can cancel our variables. So we have equals 9.8 meters per second. And we always watch out for our units because we don't want to make Miss Lee cry and we don't want to lose any points on our AP exam. Okay, so that's how we do it. And then the question is, what is our acceleration? Acceleration is actually a constant. So my acceleration in this case is going to be S double prime is equal to 9.8 meters per second squared. There's no t, so doesn't make sense to plug in a t here. So that's A. Easy. Next, what is the ball's speed and acceleration 3 seconds after drop? You just do the same thing, but you plug in 3 instead of 1. It says sometimes this equation is written as h equals negative 4.9 t squared. Explain why this variation exists. Now, this is actually a really interesting question because it forces you to kind of understand what your different parts are. But let's kind of break it down. Let's work with our original problem. S equals 1/2 9.8 meters per second squared t squared. So this is my position function. And then what we can write instead is we can write S equals 4.9 t squared and meters per second squared t squared. So the difference between this and the variation is that there's a positive and negative. And as I mentioned previously, this one here is assuming that your position is supposed to be moving down. Gravity always pulls down, so that's why we're assuming the correct direction is down. So my positive direction is down. Whereas this one that we're given over here, we're assuming that my positive direction is up. So as gravity's pulling it down, that's why we get that extra negative. But again, basically all this is saying is you have to know the context of your positives and negatives. Now, last question, it says prove that the ball is always speeding up. Now, one of the things that we talked about previously is that speeding up means that the acceleration and the velocity are both positive or negative. So that's what we're going to be checking here. So let me erase this really quickly. And then it says prove that the ball is always speeding up. So this is going to be D. And then basically what we're going to do is we're going to say S prime is equal to 9.8 meters per second squared t. You know, we're going to leave the units out just to make this a little bit neater for now. You are allowed to kind of do that when you're just working with these general equations and you're not working with it contextually necessarily. So it's S prime equals 9.8 t. And then what we can say is S prime is always positive for t greater than or equal to 0. And it only makes sense to take that because we're not going backwards in time. So for all of the cases that we care about, this is always going to be positive. Similarly, S double prime is equal to 9.8, which is, so S double prime is always positive for t is greater than or equal to 0. And then so our conclusion, and again, we do want to set this up because we do want to kind of lay down our groundwork. Just because it's in our given doesn't mean that we want to just assume it. We have to kind of state it. So what we can say is S prime and S double prime are both always positive for t is greater than or equal to 0. So it is always speeding up. And just as a reminder, speeding up basically means that my speed and my acceleration are both either positive or both either negative. Sorry, I'm not sure why I'm having so many technical difficulties tonight. All right, let's work with another problem. It says this. A blast blows a heavy rock straight up so that the height can be found using h equals 160t minus 16t squared, where the height, h is height and t is time after blast. How high does the rock go? What is the speed when the rock is 256 feet above the ground? Does this equation hold for any t? If not, what t values does this not work for and why? So again, basically we're seeing, do you know the context of your derivative, your second derivative, as well as do you understand the context for what the problem should be saying? So first thing, it's asking how high does the rock go? So this is my position. And if you're really slick, you'll kind of notice that it's a parabola. So if you had to guess what the highest position is, you're going to figure it's at the vertex. Now, if you're not, if you wanted to kind of figure this out using calculus, what you can kind of figure out is that if you do h prime, you're saying what is the rate of change of your height. So if your rate of change is positive, that means your height is going up. But the second your rate of change is negative, that means that you're starting to decrease in height. So with that contextually, basically what we're looking for is h prime is equal to 0. Find the t. That's what we're trying to find here. That's what question 1 is asking. How high does the rock go? Again, you're basically looking for when does this maximum occur? When do I stop increasing and start decreasing? Secondly, what is the speed when the rock is 256 feet above the ground? And again, the way that you guys figure that out is you have to just plug in, well, this is my height. What is the t that the height is going to be equal to 256? So figure out what the t is, and once you know what the t is, then you can just plug that into your h prime. And finally, does this equation hold for any t? If not, what value does this not work for and why? And basically what you're trying to do here is you're trying to think, okay, where would this break? Now, t is time after blast. So this is telling you that the height is changing in a parabolic motion, and that doesn't make any sense before the blast. The rock isn't magically moving. The blast is what kicks it off. So it doesn't make any sense to say that t can be negative. So that's why we're going to say t is positive. But at the same time too, just thinking about how a rock moves, if it goes up and eventually comes down, it's not going to just keep dropping forever and ever. It's eventually going to stop, and it's going to stop when your height is 0. And so that's kind of what we're going to be looking for there. So again, all of these, we're kind of contextually thinking, we're physically thinking, and we're trying to think, okay, what's going on here? How does this work? And that's a really big part of these calculus type problems. So let's go over it really, really quickly. Again, first we're just pre-thinking like that. So number one, how high does the rock go? So what I'm going to find is where is h prime equal to 0. So from there, I'm going to get 160 minus 32t equals 0. So then I'm going to get 160 equals 32t, which means that t is equal to 5. So this is where I stop increasing and I start decreasing. If you're not sure if this is the actual case, what you can do is you can always do a sign chart, and then you can kind of see, like, from here we can go like this. This is 5. This is 160 minus 32, or really honestly what you could do is you could just go 5 minus t, and then from here it's negative and then positive, where t is less than 5 and greater than 5. Again, this is one of the things you can do for verification. Again, don't worry too much about the nitty-gritty of the mechanics, because right now this is just our first look. Once we start getting to integrals or antiderivatives, then we're going to start talking about how to actually find maximum, how to actually find minimum, how to use all of these things a little bit more fluidly. But right now it's just, again, it's a first look. It's just a kind of, okay, do we get the general idea? So if you're like, what, I don't get that, that's fine. As long as we're kind of getting the idea of, all right, what's this asking? So that's number one. Number two, it says how high does the rock go? So now that we found our t, we have to figure out what the actual height is. So it's going to be 160 times by 5 minus 16t squared, or 16 times by 5 squared. And let me pause so I can plug in my calculator. So your height is going to be equal to 400. Next, number 2. And technically it doesn't actually tell you that h is height, but it doesn't tell you that it's feet. It doesn't tell you that time is seconds. So technically this is just a poorly written problem. My bad. Next, what is the speed when the rock is 256 feet above the ground? So basically we're going to go 256 equals 160t minus 16t squared, and then we're just going to solve for t. Okay, so once you do your quadratic, you're going to figure out that t is equal to 8 and 2. And just thinking about this physically, again, basically what that means is as it's going up, after 2 seconds, it hits 256 feet. It goes all the way to 400 feet, starts coming back down, and is at 256 feet, again, after 8 seconds. So now it's asking me what our speed is, so let's kind of plug that in to our h prime. So we're going to say 160 minus 16 times by 8 is equal to h prime of 8. And then we're going to say 160 minus 16 times by 2 is equal to h prime of 2. And again, this is how we're going to be figuring out our speeds. Now, most likely you caught it, but I accidentally wrote 16 instead of 32. I forgot to derive the t squared properly, so I didn't use my exponent rule correctly. But basically what we're going to get is h prime of 8 is equal to negative 86, and h prime of 2 is equal to 86. So if the question is, what was the speed when the rock was 256 feet above the ground? The answer is 96 feet per second. Now, assuming that it's feet and second, even though this question didn't give you that, because most likely I just forgot to copy that part down. But again, this is kind of what's going on over here. We're saying 96 feet per second. And the reason why we made this positive is, again, it's asking for speed, not velocity. Velocity asks for direction. So if it did say what was the velocity, when the rock is 256 feet above the ground, you would have to include negative and positive. But that's why making sure you're reading the question is very important. Finally, does this equation hold for any t? If not, what values does this not work and why? And then number one, we said it shouldn't work where t is negative. And the second place is once it hits the ground, this ceases to work because the height is just 0 once it hits the ground. So then we can just figure that out by saying h is equal to 0. So let's kind of figure that out. So it's going to be 160 minus t squared equals 0. 160t. And then 16t squared equals 0. And then from here, we can just divide everything by 16. So we're left with 10 minus t equals 0, which means that 0 and 10 are our answers. So that means it does not work for t is greater than 10. Again, apologies that my mechanics are so sloppy. It is a little bit late, so I'm just kind of trying to rush this video out. And the main thing is just we're trying to get used to the main idea of like, oh, what's it asking for, and just getting that first look. That's the main thing that we're trying to work on right now. All right, now adding on to this, there's a really common question that's often asked. It says, what is the average velocity of the rock from the time of the blast to t equals 10? Now, the reason why I hid this question earlier is because if I included this, it'd be pretty easy to kind of assume that it does not work after t is greater than 10. But it says average velocity. Basically, it's saying average velocity is equal to end minus start all divided by time. And in this case, the context is we're saying position minus position divided by time. My starting position was 0. At t equals 10, it's 0. And the time it took was 10. So my average velocity is 0. Again, this is one of those kind of quote-unquote trick questions where it feels really wrong to say it, but it does kind of pop up every now and then, especially in multiple choice questions, because it's forcing you to figure out like, oh, hey, yeah, average is not always the best way to decide things, and especially when you're taking a really distant average, so like over 10 seconds. If it was like 0.2 second average, it's not the end of the world, but when you're taking these really big averages out of context, it can feel very weird. All right, now this is one where a lot of you guys mentioned that you guys had trouble with, and this was our graphing. So it says this: given the graph of the particle's position on the y-axis, where the y is position, x is time, please graph the function please graph the derivative function, then its acceleration function. So what I'm going to do is I'm going to graph your derivative function in red, and then I'm going to graph your acceleration function in blue. Now, basically, if you remember what the derivative function is it's the rate of change. So if I'm looking at this section over here, I'm really just looking at what is the slope. At this point, what is the slope? At this point, what is the slope? At this point, what is the slope? So on and so forth. And if you notice, I rose 1 and I ran 2. So for all of these, I have a slope of 1/2. So from 0 to 2, my slope is a constant 1/2. So from 0 to 2, my slope is a constant 1/2. And the thing that we have to be careful of, though, is these are open circles here. Now, I'm going to put myself away so that way you guys can fully see this a little better. But again, the main idea here is we're saying, what is the slope at 0? What about 0.1? What about 0.2? What about 0.3? So on and so forth. At 2, we cannot take the slope there because there's that cusp, there's that little corner, and we're not allowed to take the derivatives at the corners. That's why there's these open circles. Now, following on with that logic, then we're going to say, okay, what is the slope from 2 to 4? And then what we did is we rose 4 and we ran 2. So my slope now is 2. open circle to open circle. And then what is my slope from here? And again, it's going to be 0. Open circle, open circle. And again, all we're doing is we're saying, okay, look at my graph and figure out the slope. And then we're just going to graph that on there. And then finally, we're saying from 6 to 9, I'm going to drop a total of 5, and I'm going to run a total of 3. So it's going to be negative 5 over 3, and I should have included this a little bit more, but it's basically going to be down here. But again, that's your general idea. You're just saying, what is my slope and how do I graph it? What is my slope? How do I graph it? So this is your derivative function. And then they might ask, what is your acceleration function? And you're just repeating that. Remember, acceleration is just what is the slope of your derivative function. So what's the slope of this portion over here? The slope is obviously 0. What about the slope here? Well, the slope is again 0. The slope is 0. The slope is 0. But we still need to keep these open circles. And the reason we keep the open circles is there's no slope here because it's not continuous. So again, when we're doing graphing, all we have to remember is that derivatives are rates of change or derivatives are slope. So we're just seeing for this section, what is the slope? For this section, what is the slope? For this section, what is the slope? And that's kind of how these graphing problems work. Okay, so in summary, please be careful. There's a difference between instantaneous rate of change and average rate of change. If you're doing average rate of change, just take the endpoints, divide it by the time change. It's just your slope. You take the derivative when you're doing instantaneous. Make sure you know the difference between speed and velocity, and especially when you're dealing with context, you're trying to figure out, hey, where's my positive, where's my negative, what's my direction going? And when you're doing slopes, or when you're doing speed, just always take the absolute value of your velocity. There are a bunch of classic problems. There's particle motion, free fall, population growth, depth or height change in water where something's filling or draining in a container. But again, we'll talk about these a little bit more as time goes on and I'm giving you actual AP exam problems. But again, most of these AP problems come from when you're doing antiderivatives as well. Like it puts all of them together. Make sure you know the context. One of the most common ways to make mistakes, I think on the 2004 AP exam it does this, on the 2006 AP exam it does this, and I know on the 2010 AP exam it did this, where basically what it did was the function it gave you is it gave you a growth function. So the function that you started with wasn't your position function, it was your rate of change function. So when it asked you what is the rate of change or what is the speed, you didn't take the derivative, you used your original function. And that's why those antiderivatives are important, because if I asked you what's the position, you had to go backwards. So be careful, context is important. Also the positives and negatives are also important because that gives you direction. Okay, finally, don't forget what derivatives represent. So when you're graphing, make sure that you just know, hey, I just look for the slope and graph that out. And be very careful whenever you're dealing with those little like corners and cusps and stuff. There's always an open circle there because you cannot take the derivative there. Okay. Sorry that this video was not the most polished thing in the world. Again, sorry that I was absent yesterday. I was just a little bit sick. If you guys have any questions, let me know. If not, hopefully good luck on your homework. Like I said, the main thing is just to start to get our brains thinking with this one. We're really going to get good at this once we start doing antiderivatives, because that's where most of those questions come into play. So it's not worth like stressing over until then. Okay. If you have any questions, let me know. If not, I'll see you guys later.